This is problem 5A12. So in 5A12, we're given this disk rolling with no slip conditions to the right here. We're given the mass, radius of gyration, big R, little r, and the applied force at an angle theta. So the problem is asking us to find the angular acceleration of the disk as a function of theta. For step 1, we need to draw the free body diagram. So as you can see here, I drew the weight force in the negative j direction and the normal force in the positive j direction, both through the center of gravity of the disk. The friction force is applied to the bottom of the disk along the surface to the right, because this no slip condition is actually helping our acceleration in the I direction, so we want it to be with movement. And then the applied force here at an angle theta as given in the figure. So writing the coordinate system, we just write I in the x direction and j in the y direction. The forces then need to be written out in vector form. So as I explained here, weight force is in the negative j direction with a quantity of mass times gravity, and then normal force in the positive j direction, friction force in the positive I direction, and this applied force is F cosine theta I plus F sine theta I at this angle theta. Next, we write out the acceleration. So we know that at the center of gravity, the disk is moving to the right, so the acceleration is purely in the positive I direction. So we have AGX here in the I direction, and that is it for our acceleration. Next up, we apply Euler's equation. So I simply plugged in all the forces on the left and multiplied this AGX times mass for the right side of the equation. And then after that, we split that up into I and j components. And this will give us equations 1 and 2 that we'll use to solve later. After that, we need to apply Euler's equation, which is stated there. So at the center of gravity, we can simplify Euler's equation to the sum of moments equals the moment of inertia at the center of gravity times the angular acceleration. So our sum of moments here will be for our two forces working at a moment arm about g. So our friction force is working about g from the big R. So our friction force will be F times big R, and then the applied force is working at a radius of little r, so that'll be F times little r. And then the moment of inertia about g is mass times the radius of gyration squared. After that, we have to plug in some equations from past chapters because we have so many unknowns in equations 1, 2, and 3 here. So I did the acceleration at the center of gravity compared to the acceleration at the place where the disk touches the surface right here, where we know that the velocity is 0 and the acceleration is towards the center of gravity, so straight upwards. So plugging in for these, we know the acceleration at the center of gravity, and as I just stated, we know the acceleration at c. So we just need to do the cross product of the angular acceleration times the position vector from g to c, which we see here is just simply big R. And then solving for that, we will get equations 4 and 5 when we split that into I and j components. So this equation here is kind of hard to see, but it's just that there. So then after that, we have all of our equations now, and we just need to solve for the unknowns. So I'm starting here with equation 1 that we found from Euler's equation. So in this equation, we have the unknown friction force, and we have the unknown AGX here. So to solve for those, first I plugged in equation 4 for AGX to find that is the angular acceleration times big radius r, and then I plugged in equation 3 to find the rest. So then after that, you just solve for angular acceleration here, and the final answer symbolically of this problem is the force times little r minus big R cosine theta over m times big R squared plus the radius of gyration squared, and that is in the k direction.